Welcome to Basic Mathematical Analysis class. Today we will discuss what is tail of a sequence and how to show that some sequences cannot converge. As a note, how to show a sequence is not converging. How to show certain sequences cannot converge. So we know that by definition of convergence, for a given epsilon greater than 0, we want to find some k of natural number such that your modulus of xn minus x is less than epsilon for every n greater than or equal to k. So when this condition is held, means we will say that your sequence xn converges to x. So in order to show that sequence is not converging, what we have to show? So in order to show that, a sequence x equal to xn does not converge to a number x it is enough to produce at least one epsilon, one number epsilon greater than 0 such that no matter what natural number k is chosen, one can find a particular nk satisfying this nk greater than or equal to k such that modulus of x nk minus x is greater than or equal to this epsilon. Okay, so when you're taking this epsilon naught, you should take here as epsilon naught. So this is the condition, that is, in order to show that a sequence is not converging to a given number, what we have to list it out is at least one value of epsilon such that we cannot find a natural number k such that modulus of xn minus x is less than that epsilon. For example, 3.17 example. The sequence 0 2 0 2 extra 0 2 extra does not converge to 0. 0. And it does not converge to 2 also. First we will show that this is not converges to 0. How to show? For that we should take an epsilon, right? So let I'm taking epsilon is equal to 1, right? Epsilon is equal to 1. Then suppose I'm taking my n to be as an even number, an even number. Even number. Then what will happen? So whenever I am having modulus of xn minus x or xn minus 0, here 0, xn minus 0 means it should be, my xn means even, n is even. When n is even means it should be 2. So 2 minus 0, what I'm getting is 2. So in this case we cannot say that this value is less than epsilon, which is not less than epsilon, that's equal to 1. So it does not converges to 0. Again, it does not converges to 2 also. What's the reason? Suppose again I am finding my epsilon is equal to 1 and you take n to be as an odd number. Then what will happen? Modulus of xn minus 2 I want to take. Now whenever n is odd, xn is going to be from the sequence n is odd, 1, 3, 5, everything is 0, right? So when n is odd means what I am getting is 0 minus 2. 0 minus 2 I will get. Now 0 minus 2 I am taking modulus, so I am getting 2. Now this 2 also not less than epsilon is equal to 1. So this implies your xn cannot converges to your x or 2, right? So this sequence cannot converges. In the same fashion you can check for some other sequence also. In your textbook it is given one more sequence. Consider the sequence. Second example. Consider the sequence 1, 2, 3, extra up to n extra, right? This does not converges to any x belongs to R. That means this sequence cannot converges. This sequence diverges. So how to prove it is diverges or it is not converging? So here our sequence is xn is equal to n, right? Now suppose the sequence xn converges to some c, okay, for some c belongs to R. Now if you are getting a contradiction means we can conclude that this xn cannot converges to any of this real number. Now we have assumed that this xn converges to c. Then modulus of xn minus c is less than epsilon for some n greater than k, right? Comma, this k belongs to natural number. That is, what I'm getting is mod n minus c is less than epsilon, which implies and implied by minus epsilon less than x minus c, sorry, not x, this is n, right? N minus c less than epsilon, or that is what I'm getting from this quantity. N is less than c plus epsilon. What is n? Natural numbers, right? For some n greater than k. So what does this implies? This implies your n is bounded, right? Or which implies set of natural number is bounded. Set of natural numbers is bounded. Is it bounded? No, right? So we are getting a contradiction. That means our assumption is wrong. So which is a contradiction? Which is a contradiction. Therefore, our sequence n cannot converges. So we can easily say that it's not converges. Now we will pass to our topic, tail of a sequence. Tail of a sequence. T-A-I-L. Tail of a sequence. Now, tail of a sequence means, first of all, let us have some example. Then I will define it formally. So, consider the odd numbers 1, 3, 5, 7, 9, 11, 13, etc. Now, if I'm saying that this is a sequence, right? So, my sequence is this. Call the sequence as X. Now, I will mention X10 or take some more x5. Okay, let me take it as x5. So when I'm taking x5, it is said to be the fifth tail of the sequence. Okay, in general we will say that xm means m tail, so it is 5 tail, right? What you have to consider is this is again a sequence by 1 2 3 4 5. So start from here. From here onwards, what you are getting? So you're getting 11, 13, next element should be 15, etc. Right? Now this is called the fifth tail. So two tail means 1, 2. Then it will start from 5, 7, 9, etc. Can you follow now? So m tail means after the mth stage onwards the sequence. So its definition 3.1.8 definition. If x equal to x1, x2, etc., xn, etc. is a sequence of real number, is a sequence of real numbers, and if m is a given natural number, is a given natural number, then the m tail, then the m tail of x is the sequence xm equal to, I should start from m plus 1 onwards, right? So I'm writing xm plus n such that n belongs to n. Or I can list it as xm plus 1, xm plus 2, etc. Right, so this is the formal definition of the m tail. If x is a sequence with the x1, x2, x3, etc. are the terms, then a real number, a natural number m is given, then the m tail of that sequence means you should start from m plus 1th element of the sequence and form the sequence. Now here is the theorem. So the problem is that suppose you have got a sequence, okay? So here so many members from the sequence. I'm taking as x1, x2, x3, x4, xy, x6, x7, etc. Okay, this is my sequence x. Now suppose I am considering a 5-tail, right? So my xy. So xy is x6, x7, x8, etc. Now suppose this sequence is converging to a point A. Now what about this sequence? Will this sequence be, that is the m tail or the 5-tail, will converge? Is it converges? Is it converges? Or is it converges to A itself? This is our question. Can you follow? If a sequence is given and that sequence is converges and that limit is going to be some number A. Now we can go for taking on the m tails, that is the 5-tail, 10-tail, 100-tail, like that. So many tail of the sequence you can consider. Now our question is, will this tail of the sequence converges? And if so, will it converges to the same limit as the sequence x? So here is a theorem which will answer us, yes, it will converges to the same limit. 3.1.9 theorem. Let x equal to xn, n belongs to n. Be a sequence of real numbers, and let m belongs to n. For taking the tail of the sequence, you are taking n belongs to n. Then the m tail, is, I'm denoting as xm equal to xm plus n such that n belongs to set of natural numbers of x converges if and only if x converges. In this case means whenever the sequence converges, limit of xm should be equal to limit of x. So can you follow the theorem now? X be a sequence of real numbers and we are taking is m tail, then x converges if and only if its m tail is converges. Or in other words, if m tail is converges, then x is also converges. and if x converges, then m tail also converges to the same limit, and whenever the tail of a sequence converges to a limit, then the entire sequence will converges to the same limit. Proof. First, we will note that when you are taking a m tail, that is, suppose we are having the sequence xn as, I'm setting set of even numbers, right? So this is my sequence. Now suppose I'm taking this as my x, and suppose I'm taking the 4 tail. So 4 tail means 1, 2, 3, 4. So I should start with 10, 12, 14, 16, etc. Right? Now you can say that in the m tail, this 10 is going to be the first element. But in xn, it is going to be the 1, 2, 3, 4, 5, fifth element. That is 4 plus 1th element when you are taking m tail. Now, suppose I am going for like this. Suppose I am taking the x100. Then what should be my first term? Definitely my first term should start with 202 itself, right? So x100, then 202, 204, something like that may come, since I'm taking even numbers. Now 202 will be occurring as in the sequence as 100 plus 100 plus 1th element, right? That's 101th element. So like that, the relation. Now suppose you know the term in the m tail, you can find what is the position of that element in the original sequence. Now from the original sequence also you can find what is the position of that element in the m tail also. So first we will note this relation. Note that for any natural number p, for any natural number p, the pth term of xm is the p plus mth term. P plus mth term of x. P plus mth term of x. Similarly, here we have gone from m tail to the sequence. Similarly, if q greater than m, then the qth term of x, qth term of x is q minus mth term of q minus mth term of xm. So we have noted the relation. Now we want to prove if x converges, then m tail also converges. Now assume x converges to some x, which implies given any epsilon greater than 0, there exists a natural number k epsilon belongs to n such that modulus of xn minus x is less than epsilon for every n greater than or equal to k of epsilon. Now for this k greater than or equal to k of epsilon minus m, what will happen? The terms of xn, the terms of x m will satisfy mod x n minus x less than epsilon for every n greater than or equal to. So what does this means? See, what I am taking is, suppose we have got a sequence here. Okay, my sequence is x1, x2, x3, etc. Okay, now I'm taking the this is my sequence x. I'm taking xy, and suppose this sequence converges to some x. Okay, now we're taking xy. So xy means a sequence should start with x6, x7, etc. Right. Now suppose this x converges to some point x, and for some epsilon greater than 0, suppose I have got my k of epsilon as 12. So after the 12th stage onwards, the sequence having modulus of x minus xn is less than this epsilon. Now I'm taking k of epsilon as 12 means I can go for 12 minus 5, that is 7. Now this 7 will satisfy for xy. So after the 7th stage onwards, I'm having modulus of xn minus x is less than epsilon for all the elements in x5. So this is the meaning. So I can have here my natural number as 7 here. Okay, previously it was 12. So in the same way here, we have started with k of epsilon, that is x is converges. So we are having a natural number. Now from this natural number, we have got for xm a natural number k. So now for k greater than or equal to k of epsilon minus m. So I am taking that value, k of epsilon minus m. The terms of xm, will satisfy modulus of xn minus x is less than epsilon for every n greater than or equal to k. Thus we can take km of epsilon for the m tail is equal to k of epsilon minus m, so that your m tail xm also converges to some x. Now we want to assume we want to prove the converse part. Conversely, if xm converges converges. Then for a given epsilon, we have modulus of xk minus x is less than epsilon. Xk minus x is less than epsilon for k greater than or equal to km of epsilon. Then for n greater than or equal to km of epsilon plus m, right? Because you are taking in m tail, so in the original sequence it should be km epsilon plus m. Satisfy modulus of xn minus x is less than epsilon. Thus we can take k of epsilon, that for the original sequence x is equal to km of epsilon plus m. Therefore x converges if and only if converges to x, right? I missed that one. Converges to x if and only if xm converges to x. Hope you understood this. Now one more remark is the a sequence x1, x2, x3, etc. is said to be ultimately constant. Ultimately constant. Ultimately constant, or we will say that eventually constant. Eventually constant if xk equal to c, comma, a constant for k greater than or equal to n for some n belongs to n. So for example, consider a sequence 1, 2, 3, 4, 5, 6, 7, 7, 7, 7, 7, etc. This is an eventually constant or ultimately constant sequence. That means after a certain stage, I'm getting everything as a constant. Now, evidently, every constant sequence is ultimately constant sequence, right? When you're writing 1, 1, 1, 1, 1, 1, 1, it's a constant sequence. And after a certain stage means the first stage itself, it is everything is going to be constant. So a constant sequence is always an ultimately constant sequence or an eventually constant sequence. Now the exact definition of ultimately constant or eventually constant sequence means after a particular stage all the elements in the sequence are constants. Thus, this ultimate term we can use for anything which is coming after a certain stage. Everything is going to be having a common property, means we will say that it's the ultimate property or something. Okay, thus a sequence x converges to x can be expressed in terms of this ultimate property. Thus a sequence X converges to X if and only if the terms of X terms of capital X are ultimately in every epsilon neighborhood of X, every epsilon neighborhood of X. Is it clear? A sequence converges to X means what you are writing? Modulus of xn minus x is less than epsilon. That means your xn is lying in the epsilon neighborhood, right? So whenever a sequence converges means, what does mean is, you take an x, take an epsilon neighborhood, that is this your epsilon. So when you're taking this epsilon neighborhood, all the terms of the sequence lie in this epsilon neighborhood. So after a certain stage, right, for every n greater than or equal to some k of epsilon we will say. So after a particular stage, every term of the sequence belongs to some epsilon neighborhood. So we can say that it belongs to and ultimately in every epsilon neighborhood of X. So with this, I'm winding up today's session here. Thank you for your patient listening. Thank you.